Hello and welcome to week 2 of Math 211. This week we will continue our discussion of vectors, and in particular we are going to extend the ideas that we worked on last week with vectors to the domain of multiplication of vectors. So recall from last week that we defined addition and subtraction of vectors geometrically and algebraically using the component form of a vector. This week, we are going to define multiplication of two vectors, and we're going to do this in two ways. The first being what we call the dot product. That's going to be our concern right now. And then we'll move on to the notion of the cross product. So again, there are two ways to multiply vectors, each with a unique notation and definition. The first form of multiplication that we'll look at is what is called the dot product. And to just start things off, we'll go ahead and define the dot product of two vectors, v and w, in the following way. Note that these vectors are in three-dimensional space. We could also define the dot product in two-dimensional space. The dot product is computed by multiplying the individual components together and then adding them. Let's look at an example to see how this works. The first example here, we have two vectors, v and w, and we just want to find the dot product. Practice using this particular operation. So we have that the vector v multiplied by, in terms of the dot product, the vector w, is going to be equal to, we have that 1 is v1, we have v2, v3. Here we have w1, w2, w3. We multiply and add the components together. So for v, we get 1 times -5 plus v2 times w2 is going to be 2 times 0. And last but not least, we have 3 times 7, our v3 times w3. After a little bit of multiplication, we end up getting -5 plus 21, which is going to be equal to 16. This is a straightforward computation of the dot product, just going off of the definition. Before we give an interpretation for what the dot product represents, let's go ahead and look at some properties of the dot product given its definition. Given three vectors, v, w, and u, the following 5 propositions are all true about the dot product. Each one of these is relatively easy to prove using our component form for each vector. So for example, in v, we would have v1, v2. You can even do this in v3. Note that here we're saying the dot product is in R3, but again, we can switch this to R2. R2 being our two-dimensional space, the regular Cartesian plane. I'm not going to prove all of these statements, but I will go ahead and prove one of them, that being proposition number 3. Let's go ahead and see what this proof would look like. We want to show that v dot w plus u is equivalent to v dot w plus v dot u. That is, that the dot product distributes into this sum. Remember, the dot product is not standard multiplication in the way that we've seen before. We have a special definition for what multiplication is for these things that are very different than scalar numbers. They're vectors. So to prove this statement, we go ahead and start off with knowing that we want to examine v dot w plus u. It'll help to use the component form in order to prove this statement. We get v dot, first off, in the brackets, we have w plus u. And in the component form, that would leave us with w1 plus u1, comma, w2 plus u2, comma, w3 plus u3. Closing off that component form, we have the following. Now remember, we want to compute the dot product, so that is going to give us v1, v2, v3, dotted with w1 plus u1, comma, w2 plus u2, comma, w3 plus u3. Now we can apply the dot product. Using the definition, we have v1 times w1 plus u1 plus v2 times w2 plus u2. What we're doing is we are multiplying the components in each individual piece. Lastly, v3 times w3 plus u3. Now we can use a little bit of algebraic manipulation, distributing v1 into the brackets, v2 into the brackets, v3 into the brackets. Once we do that, we can reorganize algebraically a little bit and see that this will end up giving me my desired result of v dot w plus v dot u. I encourage you to try to prove the rest of the statements on your own. It's a good exercise to get used to using the definition, especially in the context of abstract general vectors. While we had a geometric interpretation for addition of two vectors, we don't have any idea what the dot product represents in the context of geometry of vectors. All we had was a definition and a computation definition that we could use to compute and do certain proofs. Now we're going to shift to an interpretation of the dot product geometrically. To make things easier, I'm going to stick to vectors in R2 rather than R3 because it's going to be easier to draw pictures. While we had a geometric interpretation for addition of two vectors, our definition of the dot product thus far is purely computational. Now we're going to look at a geometric interpretation. Unfortunately, the proof is quite technical and I don't want to spend time in this video going through it. If you're interested, I encourage you to look at your textbook for a detailed proof. For now, we'll look at some pictures and motivation to help us understand what the dot product is geometrically. To start, we're going to begin with two vectors in R2. We could do this in R3, but it's just going to be more complicated to draw, so we'll stick to R2. Suppose that we have a first vector, which we're going to call W, and a second vector we'll call V. So here is W, and here is V. Notice that between these two vectors, we have an angle between them, call it theta. Now, we can draw a picture similar to what we did when we were dealing with the addition of two vectors by seeing that if I have a vector here, that W plus whatever this vector is should give me my vector V. What vector is that going to be? That would be the vector V minus W. We would have that W plus V minus W would give me my vector V. In order to have a relationship between these three vectors and the angle theta, we need to use the law of cosines. We have a triangle, we have an angle, and we can relate all of these together using the law of cosines. As I said, the proof isn't terribly difficult, but it is quite technical, and it's why I don't want to spend the time to work through that proof. But again, the law of cosines can be used to develop a relationship. That relationship is given by the following theorem, which relates the dot product to the angle between the two vectors, theta. The theorem states that if theta is the angle between two vectors, v and w, again, these two vectors could be in R2 or they could be in R3, then the dot product of those two vectors is going to be equal to the magnitudes of v and w multiplied together times cosine of theta, where theta is the angle between those two vectors. Let's put this theorem into practice. Here we're given two vectors, v and w, that are both in three-dimensional space. We can use this theorem to find the angle between them, as is stated in the problem. In order to do that, we are going to need the magnitudes of each of those vectors. So we would have that the magnitude of vector v is going to be the square root of 3 squared plus 2 squared plus 1 squared, which after simplifying will give me the square root of 14. Similarly, we compute the magnitude of the vector w, which is going to be equal to 1 squared plus 3 squared plus 4 squared. Simplifying gives me the square root of 26. I'm not going to go ahead and simplify these radicals. We can just leave them as the square root of 14 and the square root of 26. Now, using the theorem, we know that v dot w, we have the definition of the dot product, and using the definition, we would have 3 times 1 plus negative 2 times 3 plus 1 times 4, and after some simplification, we would get that this would be equal to 1. Now we can use the theorem. We would have that 1 is going to be equal to the square root of 14 times the square root of 26 times cosine of theta. Thus, we know that we would have that cosine of theta equal to 1 all over the square root of 14 times the square root of 26. Then we can do a little bit of algebra and determine that theta is going to be equal to cosine inverse of 1 over the square root of 14 times the square root of 26. If we plug this into a calculator or an online analysis program, we would go ahead and find that cos inverse, or arc cosine, of 1 over the square root of 14 times the square root of 26 would be approximately 87 degrees. Now that we have a relationship between the dot product and the angle between them, we can start talking about special angles between two vectors. A definition that we will run into very often is the definition of two vectors being orthogonal. So we say that two vectors are orthogonal, or really just perpendicular, if the angle between them is pi over 2, i.e. 90 degrees. Then we can relate this to the dot product. How? Well, we know that if those two vectors are going to be perpendicular, then that is going to happen if and only if the dot product is equal to 0. Where do we get that from? Remember that our previous theorem told us that the dot product, v dot w, was equal to the magnitude of v times the magnitude of w times cosine of theta, where theta is the angle between v and w. If the angle between them is pi over 2, recall that cosine of pi over 2 is going to be 0. Thus, the dot product would be equal to 0. To show that two vectors are orthogonal, we just need to show that their dot product is equal to 0. So let's consider the following two vectors, v and w. I just realized I've got a little typo in here. So this should be V and W, not V and V. In order to show that these two vectors are orthogonal, we are going to compute their dot product. Let's go ahead and look at that. We'll use our standard definition of the dot product. Recall that V dot W is computed by multiplying together components. So we would have that V dot W is going to be equal to 2 times 3 plus 1 times negative 1 plus 5 times negative 1, which is just 6 plus negative 1 minus a 5. So this gives me in total 0 as the dot product. So we have that V and W are orthogonal. The angle between them is going to be pi over 2 or 90 degrees. While it's really easy to relate the dot product to orthogonal vectors, it's just as easy to relate the dot product to acute and obtuse angles between two vectors V and W. Let's go ahead and draw some pictures to see how that works out. We already know what happens when theta is a right angle. So if we have that theta is a right angle, we can draw the following visual. First, I know that I have a vector V and another vector W, where the angle between these two vectors is a 90-degree angle. We've proven that up above in the definition, as well as a corresponding theorem. If theta is acute, we have the following image. So for theta being acute, we do the exact same thing. We'll have a vector V. We have another vector, let's call it W, where my angle between these two vectors is theta, and theta is an angle between 0 and 90 degrees. Now, we know that that angle theta is between 0 and 90. What do we know about cosine between 0 and 90 degrees? Pause the video and think about that for a second. Again, what do you know about cosine of theta when theta is between 0 and 90 degrees? If you said that cosine of theta is a positive number, you would be correct. If theta is between 0 and 90 degrees, this implies that we would have cosine of theta to be a positive number. It would be bigger than 0. So once I have this, I know that I have my dot product, a positive number times a positive number times another positive number would give me that the dot product is going to be a positive number. That is that V dot W is bigger than 0. The last case is when we have that the angle theta between the two vectors is an obtuse angle. We could draw a similar picture where I have my vector W, I have another vector V, and I know that the angle between these two vectors, again, calling it theta, is an angle between 90 and 180 degrees. Go ahead, pause the video, and see if you can figure out what the dot product would be if the angle theta is obtuse. If you went ahead and said that the dot product would be negative, you are correct. Similar to how we worked with the acute angle, we notice that the angle theta, if it is obtuse, would result in cosine of theta being negative. Remember on the unit circle, if we have that our angle theta is between 90 and 180 degrees, our values of cosine are going to be negative. So we will have a positive number times a positive number times cosine of theta, a negative number, yielding the dot product being less than 0. There are some special angles that we could consider when looking at a vector v in either three-dimensional or two-dimensional space. Those being what we call the direction angles of a vector v. These angles are angles that the vector v makes with essentially the x, y, and z axis. But because we're talking about vectors, instead of talking about the axes, we'll talk about these special basis vectors, the standard basis vectors, I, j, and k, respectively. This can be a little bit weird to visualize. I'll try to help with drawing a picture with just the vector v and one of the standard basis vectors, j. To save some time in the video, I've gone ahead and drawn the picture of an arbitrary vector v with the standard basis vector j in the direction of the positive y-axis. The angle beta is the direction angle between the vector v and the standard basis vector j. We can use the relationship of the dot product to the angle beta to observe the following. We have that v dot j is going to be equal to the y-coordinate v2. Remember that the vector j is equal to 0, 1, 0. So when I use the dot product in the standard way, v1 and v1 and v3 are going to be multiplied by 0, leaving us just with v2. This is helpful because then I can also remember, based on our theorem, that v2 and the dot product is going to be equal to the magnitude of v times the magnitude of j times cosine of the direction angle beta. Then we can observe v in its component form and see that, well, v2 can be rewritten as the magnitude of v times cosine of beta, because we know that the magnitude of the standard basis vector is going to be equal to 1. We can do similar arguments for v1, showing that it has a value of the magnitude of v times cosine alpha. And lastly, for v3, the magnitude of v times cosine of gamma. We can note that v's magnitude is a constant. We can pull it outside as a scalar, leaving us with a secondary interpretation of v in terms of the direction angles of v. We can then use this information to help us find the direction angles of any given vector v. Here, we're given a particular vector v, 2, 3, -2, and asked to find the direction angles. In order to do that, we need to first determine what the magnitude of our vector v is. Go ahead, work through that computation yourself, pausing the video. If you got the square root of 17 for the magnitude of the vector v, you've done great. And similarly, we can note from the equivalences in the component form that the vector v, in terms of its components, if we compare v1 to the magnitude of v times cosine of alpha, we have that cos of alpha will be v1 over the magnitude of v, and we have similar representations for cos beta and cos gamma. Then we can plug in the information about this vector, noting that v1 is going to be 2 over, and then we have the square root of 17. We'll have 3 over the square root of 17. And lastly, we have -2 over the square root of 17. Then, using the arc cosine or cos inverse function on your calculator, we can find out what our direction vectors are. We have that alpha is going to be approximately 60.98 degrees. Our angle beta is approximately 43 0.31 degrees. And lastly, our angle gamma is approximately equal to 119 degrees. The final application of the dot product that we are going to examine is the notion of a projection. We have two kinds of projections. The first projection being a vector projection, and the second being a scalar projection. Interestingly enough, the scalar projection is actually a little bit easier to conceptualize, so we're going to look at that one first. Let's look at the following picture. To start off, in defining the scalar projection of W onto V, we can draw a picture. Firstly, we start off with a vector V. Let's call it this one V. And then we start off with another vector, W. So here's my vector W, and here is my vector V. I also have that angle theta that I've been working with in previous examples with the angles between two vectors. I can look at the length of my vector W and note that that length is the magnitude of W. And similarly, I have that the length of my vector V is going to be the magnitude of vector V. With projections, we are essentially looking at the shadow of a vector onto another vector. In this case, if I look at the shadow that is created when I project this length W onto the length V, I end up with what we call the component of the vector W onto the vector V. This length on V is what we refer to as the component scalar projection of W onto V. We can use a little bit of trigonometry to give a little bit more context in terms of what this distance is and how to compute it. If I take this length and then make a circle from it, I can then note that this component has to do something with cosine. I have a circle of radius magnitude of W, which is going to give me that the component form here is going to be equal to the magnitude of W times cosine of theta. We can then end up with a nice computation and relationship between the component form and the angle theta, eventually getting us to the dot product. We have that the component of the vector W onto the vector V is going to be equal to the magnitude of W times cosine of theta, which sure does look similar to the dot product. The only thing missing is that we're missing that vector V's magnitude, but I can fix that by multiplying by the magnitude of V over the magnitude of V, so essentially 1. And then we have the magnitude of W times cosine of theta. Then in the top here, we end up with just V dot W. So V dot W all divided by the magnitude of the vector V. From the notion of the scalar projection, we can get the vector projection. We'll draw a very similar picture, but here we don't have to worry about magnitudes. I start off with my vector W, and I have my secondary vector V. I also have that angle theta that is going to be between W and V. I have a projection in the same way that I did with my scalar projection, but instead of having a scalar projection, I now want to think about the vector that is in the same direction as my vector V, but has a smaller magnitude. This vector is what we are going to refer as the projection of the vector W onto the vector V. Notice that the vector projection is a vector, whereas the scalar projection is a scalar, a length versus a vector. In terms of what the projection is and how to compute it, we have the following, that the projection of the vector W onto the vector V is given by the following expression. A little bit of algebra and manipulation of terms around will give us that this is actually equal to the component projection, the scalar projection of the vector W onto the vector V times V, so and it's a times, not a dot product, just times the vector V divided by the magnitude of V. Pause the video and think for a second about what this expression actually represents. You may notice that this expression is one that we have seen before. This expression is the unit vector u that is in the same direction as our vector v. So we could have that little unit vector that has a magnitude of 1. But in order to have the vector projection of W onto V, we need to have a different magnitude, not necessarily a magnitude of 1. From that unit vector, we either need to make the unit vector longer or shorter. We need to scale the vector by a scalar. That scalar is going to be the scalar projection. So the vector projection is given by scaling the unit vector in the same direction as V by the component scalar projection of the vector W onto the vector V. I'm going to go ahead and let you go ahead and compute the scalar and vector projections of the vector B given here onto the vector A given here. Be really, really careful about the order and what is being projected onto what. It can be a little bit confusing in reading the notation of the projection because this is the projection of W onto V. Be careful, work through this computation, and when you come back, I'll have it all done. The answers that you should have gotten in this are -4 divided by the square root of 21 for the scalar projection, and you should have gotten this as your vector for the projection of B onto A. Again, be careful with the order here. As a side note, it's always a good idea to compute the component scalar projection before going ahead and finding the vector projection. Why? Because we can use the scalar projection when computing the vector projection. Again, using the equivalents up here. So that concludes our discussion of the dot product for now. We will use it moving forward as we shift our discussion to the second conceptualization of vector multiplication, the cross product. Recall that when we worked with the dot product, the result was a scalar, a constant, a real number. However, with the cross product, the resultant product is going to be a vector itself. The question that we want to answer is, given two vectors, v and w, can we find another vector that is orthogonal to both v and w at the same time? Unfortunately, in comparison to the dot product, the cross product is only defined in R3. That is, we can only evaluate the cross product for two vectors, v and w, which are in three-dimensional space. We cannot define the cross product in two-dimensional space. This is something to be careful of. Always note that the dot product is defined, so the dot product is defined in all dimensions, whereas the cross product is only defined in dimension 3. So cross product only in dimension 3. Recall that our goal is to find a vector p which is orthogonal to two non-zero vectors, v and w. Also recall that the dot product is equal to 0 of two vectors if those two vectors are orthogonal. So assuming that we have a vector p which is orthogonal to both v and w, we have the following equations. The first being that our dot product of v with p is going to be 0. And secondly, that our vector w, when it is dotted with p, will give us 0. From here, we need to do some tricky algebra to find out what the components of our mystery vector p happen to be. We do this by multiplying both sides of equation 1 by W3. On the left-hand side, we still get 0. And on equation 2, we multiply both sides by V sub 2. Then, when we subtract them from each other, we end up with the following equation. We want this to all be equal to 0. So we need to find out what values P1 and P2 are going to make this equal to 0. A natural choice is to notice that if we take our P2 to be equal to the negative of the expression star, and we take our P1 to be equal to star star. So here I'm going to have P1 to be equal to star star. Then I would get 0. I'm essentially just matching up these two terms so that they will cancel out to 0. So we would have that P1 is going to be star star V2 W3 minus V3 W2. And our P2 term is going to be the negative of V1 W3 minus V3 W1 as seen here. We can then do a little bit more algebra to show that the third component, P3, should be equal to V1 W2 minus V2 W1. This leads us to the formal definition of the cross product of two vectors v and w. Given two vectors in their component form, the cross product of those two vectors is given by the following component form vector, as was motivated in the previous slide. Again, as noted on the first slide, we can only define the cross product in dimension 3. If you are given two vectors in dimension 2, you cannot compute the cross product. You can, however, compute the dot product. In contrast to the dot product, remembering the formula for the cross product can be pretty difficult. But there is a nice way to remember it, especially if you are familiar with some of the concepts from linear algebra. The following below is a different way to represent the cross product in terms of determinants of matrices. This symbol here is what we call the determinant of a 2x2 matrix. For those of you who are familiar, you know that the determinant of a matrix is computed by multiplying across the diagonal, so V2 times W3, minus the other diagonals product, So we would have V minus V3 times W2. We do the same thing for the other component, my Y component, V1 times W3 minus V3 times W1. And finally, V1 times W2, V2 times W1. Always be careful that there is that negative that is going to pop up in the Y component of our vector. Here, I've written it in component form, whereas in this conceptualization using the determinant notation, you write everything in terms of our standard basis vectors, I, J, and K. This method might be a little bit easier for you to remember. Again, here, this is the determinant. If you want to use the determinant, you are welcome to. If you would prefer to have this version, then feel free to use that. In this example, we are just finding a computation of the cross product given two vectors v and w in three-dimensional space. You're welcome to use either form of the cross product, whether it be component or in terms of the standard basis vectors and determinants. I'll go ahead and use the latter since it's slightly unfamiliar to those of you who haven't seen linear algebra. To compute the cross product, we are looking for v cross w. So this, by definition, is going to be equal to the determinant of V2, V2, V3, W2, W3 times the standard basis vector I. How did I know this? Well, remember that our vector V and W is V1, V2, V3. My I, standard basis vector, is corresponding to V1 in writing V in terms of I, J, and K. The determinant here is going to not involve 1. We do the same thing. Here, I'm working with vector J, the second component. So whatever is in my determinant is going to be not having to do with 2. So I'll have V1 and V3 along with W1 and W3. But look, I made a little typo, not thinking carefully enough. Remember, there has to be that negative in the front there. Super easy to forget because the dot product all has pluses. There is that negative always in the second component. Finally, we have a plus. We know that we will have our component vector K. And then the determinant of V1 and V2, had to think there for a second, W1 and W2. Everything is not having to do with 3. We can then fill in our values for the various components of V and W. So we'll have the determinant of 2, 3, 5, negative 1 times my component vector I minus 1, 3, negative 2, negative 1 times my component vector J. Finally, we get 1, 2, negative 2, 5 times my component vector K. Now we just need to compute the determinants of each one of the components. In the first case, we get 2 times negative 1, negative 2, minus 15, which will give me a total of negative 17i. Then I know that I have that negative, and finding the determinant of the next matrix, we would have 1 times negative 1, minus a negative 6. So we have negative 1 plus a 6, giving me 5. So in total, I have minus 5j. And lastly, for our last determinant, we have 5 minus a negative 4. So it'll be 5 plus a 4, being 9. So lastly, I get plus 9k. If we want to write this in our component form, we end up with negative 17, comma, negative 5, comma 9 as the vector v cross w that is orthogonal to both v and w. The proof that the cross product vector v cross w is orthogonal to both v and w is relatively straightforward. And once again, we will use the dot product to help us prove this. So what we want to show is that we have v dotted with v cross w. We want to show that that is equal to 0, and it's also going to be equal to w dotted with v cross w. That is, that the vector w is orthogonal to v cross w, as well as the vector v being orthogonal to v cross w. I'll go ahead and show that the first dot product, v dotted with the cross product, is 0. I encourage you to try the second one on your own. Let's go ahead and check out the cross product, or the dot product, with v and v cross w. So we'll have that v dotted with v cross w is going to be equal to, let's go ahead for shorthand and call this equal to p equal to p1, comma, p2, comma, p3. A little bit of shorthand just to make things easier. The dot product then is going to be equal to v1 times p1 plus v2 times p2 plus v3 times p3. Now we can use what we know about the component forms of the cross product to expand this expression. It's going to get more complicated. So this will end up being equal to v1 times the first component of the cross product, which is going to be v2 w3 minus v3 w2, and we move on, plus v2. Remember that the second component is going to be the negative of v1 w3 minus v3 w1, plus we have that final component, v3 times we'll have v1 w2 minus v2 w1. Sorry for the squeeze there at the end. We can then go ahead and distribute each one of our v components into the brackets. If we do that, we will end up getting v1 v2 w3 minus v1 v3 w2. Then we get a negative v2 v1 w3 plus v2 w1 v3 plus lastly v3 v1 w2 minus v3 v2 w3. A little bit of a mouthful, but not too bad. Apparently, everything is supposed to cancel out to 0, so we should see whether or not we have some matching pairs. v1, v2, w3 matches up with this term here. Multiplication is commutative, so we can recognize that those two terms will cancel out to 0. Similarly, I have v1, v3, w2. And if we look around, we can see v3, v1, w2 here. Since one of them is a negative and the other one is a positive, those will cancel out as well. Finally, we have our last term, v2, w1, v3, as well as here, v3, v2, w3. The signs being opposite, those will cancel out, leaving us with the dot product of v with the cross product v cross w being equal to 0. Once again, I encourage you to try looking at the dot product w dotted with v cross w on your own. Always good to just get a little bit more fluency with these two. Again, you know where you're going. You should make sure that your answer is 0 at the end. Otherwise, you've done something wrong in your algebra. In defining the cross product, we defined it as a vector that was parallel to two vectors v and w for which the cross product was defined. This let us know the direction of the vector from the cross product. However, there are lots of vectors that could be in that direction, but of varying lengths or magnitudes. So the question we want to ask now is, what is the magnitude of the cross product v cross w? The following theorem gives us information to that answer. It says that the magnitude of the cross product, v cross w, is equal to the products of the magnitudes of v and w times sine of theta, where theta is the angle between v and w. Again, starting in a similar place to when we were looking at the angle between two vectors v and w and relating that to the dot product. A useful corollary of the above theorem is the following. It states that two non-zero vectors are parallel if and only if their cross product results in the zero vector. Remember, the resultant item in the dot product is a number, whereas the resultant product in the cross product is a vector. So we're saying two vectors are parallel if and only if their cross product results in the zero vector. How does this work? Recall that two vectors are parallel if and only if those two vectors are in the same direction. So if I have a vector v and another vector w that is in the same direction as v, remember that the angle between these two vectors would be 0. So if the angle between those two vectors is 0, that means that sine of theta would itself be 0. So if sine of theta is 0, that means the magnitude of the cross product is 0, which then means that the vector v cross w would have to be the 0 vector. While the theorem above has a rigorous proof, it's a little bit more useful to think of it geometrically, because the magnitude of the cross product happens to be the area of the parallelogram defined by v and w. Let's look at what that looks like. Again, remember that the cross product is only defined in three-dimensional space, but the parallelogram that will be formed is itself a surface in three-dimensional space, so we can draw it in 2D. Suppose we have a vector w. Here is my vector w, and I have another vector v. Here is vector w and vector v. The angle between them is that angle theta, as is seen in that first theorem. From this drawing, I can form a parallelogram by taking vector v and attaching it at the terminal point of vector w, and then connecting in the same way the terminal point of v to the terminal point of the v up at the top, giving me that other vector w, resulting in a parallelogram. Using our knowledge of trigonometry, we can recognize that the height of this parallelogram is going to be the magnitude of our vector w times sine of theta. Remember that we used a similar trick when we were defining the component projection of a vector onto another vector. Then we can use our knowledge of geometry and the area of parallelograms to remember that the area of a parallelogram is going to be given by the base times the height. In this case, the base of our parallelogram has a value of the magnitude of v, whereas the height of our parallelogram has a value of the magnitude of w times sine of theta. But by our theorem, we know that this is actually equal to the magnitude of the cross product vector v cross w. In the following problem, we're asked to find the area of the parallelogram formed by the points 0, 0, 0, negative 1, 2, 4, 1, 1, 8, and 2, negative 1, 4. In order to start this problem, it's going to be way easier to go ahead and plot these points to get an idea of what this parallelogram looks like in space. To save a little bit of time, I have labeled these points as A, B, C, and D, and plotted them in the X, Y, Z coordinate space. From here, we can draw a parallelogram that results from these three points together. Connecting the dots, we get A to B. Ooh, wrong pen here. So we would have our A to B. We would have our C to B, D to A, and D to C. The area that we're looking for is the area here that I'm shading in yellow. The question is, how in the world do we find this area given by A? Well, from our previous slide, we know that the area of a parallelogram formed by two vectors is equal to the magnitude of the cross product of those two vectors. In this picture, we need to find out what vectors form this parallelogram. An easy way to start out is to notice that if I look at the vector that is formed from A to B, we can label that vector as W. And I also look at another vector, the vector that is going to go from A until D, and label that vector as V. Vectors V and W form the parallelogram whose area we're looking for. The question now is, what are the vectors V and W? We can use our understanding of the component form of vectors and position vectors to help us figure this out. Firstly, the vector given by W is going to be the vector that goes from the origin to the point B. So it's just going to be given by the vector with the components negative 1, 2, and 4. So we have that vector W is negative 1, 2, 4. And in a similar fashion, we know that our vector V is the vector that goes from the origin to D. And so that is going to be given by 2, negative 1, and 4. Now, we just need to determine the cross product and its magnitude to find the area of the parallelogram. I'll go ahead and leave that computation to you. Pause the video, find the cross product and its magnitude, come back and see if you got the right answer. If you got approximately 17.234 square units, you have done your computation correctly. Here, we needed to figure out what the cross product was. We used the cross product formula in terms of determinants to find that the cross product of V with W was the following vector. Then, after computing the magnitude of the cross product, we ended up with the square root of 297, which after a short computation in a calculator gave us 17.234 square units. Thus, the area of our parallelogram A, so here we have changing my color and my size of my font, we have that the area of the parallelogram is equal to that value. Finally, we have 6 properties of the cross product, all of which are relatively straightforward to prove using the definitions of the dot product and the cross product. I encourage you to work through each one of these proofs on your own. I'll go ahead and work through number 2 to familiarize you with some of the techniques used in these kinds of proofs. So for 2, we are trying to show that when I multiply via the cross product CV times cross product W, I will end up with C times V cross W or V cross CW. Now, I'll show you why this is equivalent to this. You can easily show that this is equivalent to this. Let's go through it. Writing these vectors in component form is going to be the easiest way to help us succeed in these proofs. In the first case, our vector CV will be CV1, CV2, CV3, because we know that these vectors have to be in R3 in order to define a cross product. Then we have that this is going to be crossed with W1, W2, W3. We can then write out the definition of the cross product in terms of determinants. The first determinant that we are going to compute is going to be CV2, CV3, W2, W3, I, minus the determinant of, we'll have CV1, CV3, W1, W3, times our standard basis vector J, followed by the determinant of CV1, CV2, W1, W2, times the component vector, standard basis vector K. Now we can compute these determinants individually. In the first case, after a little simplification, we will get C times V2, W3, minus V3, W2, minus, again, C times, we'll have V1, W3, minus V3, W1, followed by our plus C times V1, W2, minus V2, W1. Also remembering that we have our component vectors I, J, and K. We can then recognize that C is a common factor in all 3 terms in front of I, J, and K. Once we factor that out as a common factor, we are going to be left with this term I, this J, this K, which, if we look carefully, each are the components of the cross product. We even have that negative that we need for the second component of the cross product. Thus, we have that this long expression is equal to V crossed with W. As I mentioned, showing that we have V crossed with CW being equivalent is similar to show. I encourage you again to try this on your own. You'll gain some fluency in terms of the computations involving these definitions.